Hello everyone, my name is Miriam and today I will be presenting my machine learning project focused on predicting the net electrical energy output of a combined cycle power plant. Throughout this presentation, I will walk you through the data analysis, model selection, evaluation metrics, and final conclusions drawn from this study. First, we must understand our data. This data set contains 9,568 observations and includes the following 5 variables: AT temperature, measured in degrees Celsius; V exhaust vacuum, measured in centimeters in mercury, representing steam exhaust conditions; AP ambient pressure, measured in millibar, affecting combustion conditions; RH relative humidity, measured in percentage, impacting the heat exchange efficiency; and lastly PE, net hourly electrical energy output, measured in megawatts, which is the target variable we want to predict. The goal of this project was to build a predictive model that estimates PE based on the environmental factors AT, V, AP, and RH. To achieve this, I first needed to prepare the data. For data preparation, I did the following. I checked for missing values and ensured all variables were in correct format. I also split the data into training, validation, and testing sets. 64% of the data was used for training the model. 16% of the data was used for validation to prevent overfitting. And lastly, 20% was reserved for testing to evaluate real-world performance. With the data properly cleaned and pre-processed, I was ready to implement and compare 2 different machine learning models, linear regression and random forest regression. The first model I tested was linear regression, which assumes that the target variable has a linear relationship with the input features. My implementation steps included training the model using the training dataset and validating it using the cross-validation to ensure robustness. The model generated a linear equation predicting P based on the 4 environmental variables. Performance was evaluated using the mean squared error, MSE, and R-squared. The results showed that MSE was relatively high, meaning the model had difficulty making accurate predictions. R-squared was moderate, suggesting that the model could explain some of the variance in energy output, but not all. The second approach that I explored was random forest regression. The implementation steps taken were: I trained a random forest model using multiple decision trees to capture nonlinear relationships between the features and the target variable. I optimized the hyperparameters, including the number of trees and tree depth, to improve performance. I also applied cross-validation to ensure the model generalized well to data. The results were MSE was significantly lower, indicating better predictive accuracy. R-squared was much higher, meaning the model captured more variance in energy output. Random forest performed significantly better than linear regression because it could capture complex nonlinear interactions between temperature, humidity, pressure, and vacuum levels. To compare the effectiveness of the 2 models, I used 2 key evaluation metrics: MSE, mean squared error, which measures how far predictions are from actual values. A lower MSE indicates better accuracy. And secondly, R-squared, which represents how well the model explains the variance in energy output. A higher R-squared means better predictive power. Since random forest had a lower error rate and higher predictive power, I selected it as the final model. For key takeaways, temperature and relative humidity had the strongest impact on energy output, highlighting the importance of environmental factors in power plant efficiency. Number 2, model comparison is essential. While linear regression provided a basic understanding, random forest significantly improved accuracy. Number 3, cross-validation ensures reliability. Splitting the data properly and validating with different methods helped in selecting the best model. Lastly, number 4, machine learning can improve energy predictions, allowing power plants to optimize performance and reduce waste. For future improvements, hyperparameter tuning of the random forest model could improve its accuracy. And then also testing other models such as gradient boosting or neural networks for better results. Overall, this project demonstrated how machine learning can be applied to real-world energy optimization problems. Thank you for your time.